Good morning, class. We are moving on to lesson 6.5, and we're taking a look at variations. In lessons 6.3 and 6.4, we took a look at different applications in algebra, things that help us to solve problems, to create mathematical models that go hand in hand with real life situations. In 6.5, we're taking a look at variations of those formulas and our methods of using them. So let's take a peek. We've got four different kinds: direct variations, inverse variations, joint variations, and then combined variations. Combined is kind of a combo of the previous three. So I've got a couple examples here. It would do you well to keep your book open as you go through these so you can kind of see what we're talking about. These examples come directly from the text. Let's take a peek. First things first, direct variation. Two related variables increase or decrease together. You'll notice this is a multiplication style. So y equals kx. K is some kind of constant of proportionality. So in a lot of these examples, you'll see the letter K. K is kind of a constant, some kind of known amount or known portion of the problem. Here's an example. Distance traveled increases as the time spent in your car increases. So D equals KT, and we're going to use R instead because that's your rate. So D equals RT, and we can see that as we increase the one, the other is going to increase. So if we make the R bigger, no matter what the T is, D is going to increase. Same with it, make the T bigger, no matter what R is, D is going to increase. So this is a proportional and direct variation. Here are a couple examples. Y equals kx. The circumference of a circle C is directly proportional to its radius R. Write the equation for the circumference if the constant of proportionality k is 2 pi. I'm just going to scoot back real quick. So again, we're looking at a y equals kx form. So we've got to figure out what y is and what our k is. We know that k is 2 pi and what x is. So here's what it would look like. C, that's the one we're trying to find, is equal to 2 pi, which is our k value, times r, which is the radius. Another example using this k x equals y situation. The resistance R of a wire varies directly as its length L. Write, that should be wire actually, I'm looking at this, my bad. Write this variation as an equation. So again, we have R equals KL. R is the thing we're trying to find, K is whatever the constant is, and L is the other piece we have, length. So to find the resistance measured in ohms of a 30-foot length of wire, assume the constant of proportionality for the wire is 0.008. Some direct relationships here. So we plug in 0.008 times 30, that's what the length is. That's going to give us R, the ohms resistance. So 0.24 ohms. In some of these problems, you're going to need to label, obviously, if we have like a word type problem, which some of them are. So make sure you're paying attention to what exactly we're seeking. Example number 3, still within this direct proportionality or direct relationship rule. Suppose W varies directly as the square of Y. If W is 60, then Y is 20. Find the constant of proportionality. So we're looking for the K part. Let's take a peek at this. W equals KY squared, square of Y and W. We can solve this out. 60 is what W is, K is what we're looking for, and Y squared is 20 squared. So K equals 400 because 20 squared is 400. 60 equals 400K. We divide both sides by 400. We get the K value of 0.15. And last example of the direct kind. The length that a spring will stretch, S, varies directly when the force or weight, F, attached to the spring. The spring stretches 4.2 inches when 60 pounds is attached. How far will it stretch when 23 pounds is attached? So this is a direct proportion. If you are in physics, you might see this one as well. S, which is stretch, equals our constant times F, which is the force. So if S is 4.2 and our F is 60, we get K, we can find a K value of 0.07. Now, knowing the K value, we can flip it on its head and solve for S, knowing that the K value is 0.07, and we want to get to 23 pounds instead. So 0.07 times 23, S is going to be 1.61 inches. So you can see once we solve for whatever our constant is, we can then use that to solve additional problems. So you'll have a couple examples like that too. All right, the second type of variation is what we call inverse variation. This is when two quantities vary inversely. As one quantity increases, the other quantity decreases, and vice versa. So in this example, if K gets bigger, Y is going to get smaller. If X gets bigger, Y is going to get smaller. If X gets smaller, Y is going to get bigger. Again, K is our constant of proportionality. Let's see a couple examples. So in the luminescence, I, of a light source varies inversely as the square of the distance, d, from the source. This kind of makes sense. The farther away you are from a light, the dimmer it's going to look. Assuming that the luminance is 75 units at a distance of 6 meters, find the equation that expresses the relationship between illuminance and the distance. So using our startup, you can see that illuminance is equal to some kind of constant over distance squared, d squared. And so to solve this, we have 75 is our luminance equals k over 6 squared, so 75 equals k over 36. You can solve this out by multiplying both sides by 36 to get 75 times 36, which is 2,700, is equal to k. And we can find then that 2,700, since we have our k value, we can now utilize this equation to solve additional distances. Suppose y varies inversely as x. If y equals 8, then x equals 15. Find y when x is equal to 18. So again, we have our y value is 8. Our constant of proportionality is k over 15. And we want to find y when x is 18. So we have to solve out for our constant of proportionality. So we multiply both sides by 15. We get k is equal to 120. And now we can take that k and toss it back into the problem using 18 as our x value, because that's what we're trying to find the y for. And when we solve this, we get y equals 6.7. So as you can see, it's basically a two-step problem. A lot of these second session or second portion of your homework is going to be these two-step style problems. On to the third type, joint variation. One quantity may vary directly as a product of two or more quantities. So again, we have our constant of proportionality k. Then we're going to have an x and a z, and we're trying to multiply those together to get a y. So you'll see equations like this. Here's one example. The area A of a triangle varies jointly at its base, b, and height, h. If the area of a triangle is 48 square inches, when its base is 12 inches and its height is 8 inches, find the area of a triangle whose base is 5 inches and whose height is 20 inches. So we have all the equipment we need to solve this. We just have to find our constant of proportionality first, and then we can solve the rest. So area is equal to k times b times h. 48 from our first set is equal to our constant of proportionality, which we don't know yet, times 12 times 8. That's where we get in our first setting. So we can solve this. 48 equals 96k. We take k is equal to 48 over 96, which is 1/2. And now we know our k value. Now this might look like, oh wait, I've seen this before. Area equals 1/2 base times height. And you probably have, but this is the method by which we find this equation. Okay. Now that we have that information, we can then plug in our 15 and 20. So the area of something that's going to be a 15 by 20 is 1/2 times 15 times 20, which is 150 square inches. Two-part problem where you are working through the two different steps. Okay. Last but not least, combined variation. One variable varies as a combination of variables. You can see here, it's basically like taking the inverse, but you're also having a direct, so you've got a bunch of stuff going on here. The example given is S equals some kind of constant of proportionality over times A over P. So the owner of Colonel Mustard's pretzel shop finds that their weekly sales of pretzels, S, varies directly with their advertising budget, A, and inversely with their pretzel budget, P. So you see our setup, we have S equals KA over P. When their advertising budget is $600 and the price is $1.20, they sell 6,500 pretzels. If you're going into business at all, or if you're looking to be an entrepreneur of some kind, this would be a good piece of information to have. So we're going to write an equation of variation, including the value of proportionality constant. That, as I said, is S equals KA over P. Direct variance with the A, advertising budget, and indirect variance with the P, pretzel price. So if we have the total amount of 6,500 pretzels, and we know that the budget is $600 times our constant divided by the price per pretzel, we can then solve this out for our constant of proportionality, and we find that K is equal to 13. And now with this equation, equipped with this equation, we can solve a couple more problems. Whoops, my slide is busted. That's okay. So find the expected sales if the advertising budget is 900 and the price is 150. Well, since we found our K value to be, let me scoot back real quick, K value to be 13, we just plug our K value in now, 13, and we can solve for any given pretzel prices and budgets and advertising. So with this being said, if S is what we're trying to find, and we know that our K value is 13, we have $900 in advertising, and we're selling the pretzels for $1.50, we can expect to sell 7,800 pretzels. Now we'll see if that actually works. But that's how we use these equations. Okay, on to example number 9. A varies jointly as B and C and inversely as the square of D. If A is 1, B is 9, C is 4, and D is 6, find A when B is 8, C is 12, and D is 5. We have all the content to set this up. A is going to be on the left-hand side of our equal sign. And then we have some kind of constant of proportionality, K. And we are jointly varying with B and C, so it's going to be K times B times C. And we're inversely going to the square of D, so it's going to be divided by D squared. Here's the setup. And as we have seen in previous examples, we're going to try to find our K value first. And then we can use that K value to solve for A when B is 8, C is 12, and D is 5. So to find the K value, we know that A is 1, B is 9, C is 4, and D is 6. We plug in those pieces and we solve it out for K. We find that K is equal to 1. Well, that's not so bad. Which means that to find the second value of A, it's going to be 1 times 8 times 12 over 5 squared. Well, 1 times 8 times 12 is 96 divided by 25 gives us 3.84. So as you can see in these problems, some of them will be word style problems that you'll have to kind of decipher the bits and pieces. Others will be simply writing down the correct expression or explaining what type of these four the example is. So take some time. Make sure you're reading through pages 286 to 292. Your homework's going to be 292 to 294, and we're doing numbers 6 through 20, which again are examples of variation between these different quantities. We're looking for either direct or inverse. And then keep in mind, we've got a quiz coming up. So make sure you're studying, review the notes, and check over your homework. If you have any questions, please let me know in an email. Otherwise, I will see you in class.